Hello, everyone. I'm Charlie Smith, Executive Director of ESIG. I also serve in a leadership role with the Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors across the globe to catalyze a rapid, clean energy transition at unprecedented scale and speed. This is being done by providing a coordinated and holistic approach to the necessary knowledge, education, and support to power system operators across the 5 action pillars. The foundation of the GPST is a group of 6 system operators from around the globe who are facing higher penetration of wind and solar inverter-based resources sooner than any other operators in the world. The 5 pillars of the consortium include research and peer learning, technical support, workforce development, standardization, and open data and tools. ESIG is the lead on Pillar 1, and more information on the GPST can be found at globalpst.org. As the lead on Pillar 1, ESIG would like to welcome you to the March monthly webinar of our joint GPST Pillar 1 ESIG webinar series. This series is an addition to the regular ESIG monthly webinar series and focuses on the GPST research agenda and associated topics being addressed in Pillar 1. Topics are presented by both the system operators active in Pillar 1, as well as members of industry and the research community participating in the GPST. An additional series of webinars on the other 4 pillars of the GPST is also being provided on a monthly basis through NREL. For those of you who would like to learn more about the GPST and how to engage, please go to globalpst.org and click on the Get Involved tab. Further information on ESIG can be found at esig.energy. Next, I'd like to go over a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distractions. For the Q&A, we will use the Slido platform at slido.com. To ask a question, please navigate to slido.com and enter ESIG4 as the event code. The instructions are also at the bottom of the screen. You'll see a thumbs up button next to the questions on Slido to allow you to cast a vote to help prioritize the questions submitted. We plan to save about 10 minutes for Q&A at the end and then wrap it up at the top of the hour. An email with a link will be provided once the video file has been posted. We also plan to provide short responses to unanswered questions after the webinar, so please don't be afraid to ask your questions through Slido. Today's topic is on evaluating major contingencies and conditions with the potential to cause power system disturbances. As you might imagine, with the changing nature of the resource mix and the retirement of conventional synchronous machines, this is a topic of increasing interest and importance to the industry. As recent events such as the Blue Cut fire and the Odessa events have shown in the US, we need to make sure everyone understands and follows the new procedures for the interconnection of new generation. We need to be vigilant about making the necessary changes as we make the transition. If not, the operating consequences can be severe. Australia is one region of the world experiencing very rapid energy transition and having to adapt rapidly to changing conditions. Today, we'll hear about the approach taken by the Australian Electricity Market Operator, AEMO, to its annual General Power System Risk Review, or GPSRR, which includes its approach to identifying priority risks based on actual incidents as well as extensive consultation, conducting detailed power system analysis of non-credible contingency events using RMS and EMT simulation tools, and evaluating solution options to mitigate risks and improve power system resilience. It will be presented by Luke Robinson, Group Manager for Modeling and Engineering at AEMO, and Dan Fracalossi, a Senior Electrical Engineer working in the Grid Performance and Integration team. Luke has 20 years experience in transmission planning, power system analysis, and system operations. Dan has 9 years experience in power system analysis, transmission planning, network design, substations, and HVDC. AEMO is a member of ESIG and also a founding system operator of the GPST, and Luke heads their engagement team. Luke is a good friend and a good friend of ESIG. I greatly value his leadership and contributions to the industry, and I look forward to hearing what he and Dan have to say. Okay, just a short reminder once again to use Slido at slido.com with the event code of ESIG4 to ask your questions. Let's go ahead and get started. Luke, I'll now turn it over to you.
Charlie, for the kind introduction, and good morning, good afternoon, or good evening to all the attendees. Thank you for joining, and hopefully an engaging discussion, and look forward to some Q&A at the end as well. Look, often the focus of power system studies for planning, connections, and operational purposes is limited to things like single element trips. So we'll often refer to those in the NEM as credible events, things like single circuit trips, single transformer trips, and so forth. These are things which are reasonably possible. We cover those in all of our power system studies, and indeed define our power system limits and constraints used by our dispatch engines to manage system security to cater for those reasonably possible events. It's increasingly important, however, to evaluate how the power system performs for more severe events. So in this presentation, you'll no doubt hear us refer to non-credible events. These are, in general terms, high impact, low probability events. Things like double circuit faults, pole power station trips, operation of circuit breaker fail and associated longer clearing times, and trip of multiple elements. In most circumstances, we're not planning and operating the system to cater for those events. However, increasingly important, particularly as the power system transforms, that we understand how it behaves for these major events, and we understand how the resilience of the power system is evolving, and we maximize that where we can. So the focus of this presentation is really to describe the approach taken in the national electricity market for how we evaluate those major events. And hopefully it will stimulate some interesting questions, and will certainly, as I mentioned, allow for some time at the end. Okay, so I would like to also just acknowledge that I'm joining you today from the lands of the Wurundjeri, and Dan from the lands of the Palawa people down in Tasmania, and just pay my respects to First Nations people everywhere. Okay, a bit about AEMO, just some context for those that may not be familiar. AEMO is a member-based not-for-profit organisation. We operate as the independent energy market and system operator for the national electricity market on the east coast of Australia, and the wholesale electricity market in the southwest part of Western Australia. We are also the system planner for the NEM, and operate retail and wholesale gas markets across southeastern Australia, as well as Victoria's gas pipeline grid. We also do have an independent subsidiary, AEMO Services, established recently to help enable transparent provision of advisory and energy services to the national electricity market jurisdictions. A little bit about the NEM. Demand in the NEM varies from roughly 11 gigawatts to 36 gigawatts. We have a total of about 62 gigawatts of generation, with a massive 18 gigawatts of rooftop solar on top of that as well. Predominantly coal-based generation, so really the form of generation is rotating synchronous machines. No nuclear in Australia, of course, but we do have a large fleet of gas and coal-based generation. Like power systems globally, we're increasingly leveraging our renewable resources, particularly in Australia, where we have excellent wind and solar resource, and we're seeing a massive uptake in variable renewable energy and inverter-based resource generation. To date, we've operated with 72% renewable penetration in October of last year, which is a record for the national electricity market, and a great achievement in itself, but still a long way to go in terms of decarbonising our system and shifting away from the retiring coal-based generators that we have throughout the NEM, particularly in Victoria, New South Wales and Queensland. Just on the next slide. So a bit more about that context of what we're seeing in the NEM. We're supporting a once-in-a-century transformation in the way society considers and consumes energy. A range of factors are really influencing and shaping the resilience of the NEM. They include operating with fewer synchronous generators online as they decommit due to market price or due to retirement. we're seeing increased power transfer through major transmission corridors as we're looking to bring renewable energy to the load centres and maximise the utilisation of existing infrastructure. We're seeing, in some cases, concentrated provision of frequency services in particular regions, which impact how the system responds to disturbances, and certainly associated with the renewable connections, an increase in inverter-based resources and including distributed energy resources, which also poses challenges for how we maintain and manage grid stability, voltage, frequency, as well as cater for evolving weather-related risks. One other element to that as well, which we'll touch on throughout the presentation, is that with those changes to the power system, we are seeing increasing application of special protection schemes or remedial action schemes, which have the opportunity to enhance the resilience of the system and cater for some of the major events that we might see, but can also create some additional risks in terms of potential for maloperation. On the right-hand side of that slide as well, just linking to AEMO's engineering roadmap, really summarising the 6 operational conditions which are shaping the evolution of the power system and how it's operated. When it comes to non-credible risks, and again, we'll use this term throughout the presentation, again, we're referring to, in general terms, high impact, low probability events. Those things which you're not operating the system to cater for, but which still do have a calculatable probability of occurring. And there's a few different ways that we'll take into account those non-credible contingency events. In the planning time frame, some examples here, network service providers are evaluating the potential for major events to lead to cascading failures, and they're planning for emergency control schemes. Again, in the NEM context, given it's fairly sparse and weakly interconnected, we do tend to rely on major double circuit corridors, particularly between regions of the NEM for power transfer. This means that double circuit trips or multiple single circuit trips have a greater potential to disrupt the system, and in the planning timeframe, network businesses are evaluating the ability to mitigate those risks by installing emergency control schemes. And then more broadly, through the General Power System Risk Review, which is a key topic of today's presentation, we're evaluating priority risks across the system and how they're managed. In the operational timeframe, there are a number of means that can be used to mitigate the potential impact of non-credible events, and that's by reclassifying things as credible. So that might be, for example, a lightning storm is adjacent a transmission corridor which is known to be susceptible to lightning strikes, where a strike to the tower could cause a backflash over and double circuit fault onto the 2 circuits on a single tower. You might reclassify that tower if you know that it's susceptible to trip during a lightning event. We also do have in the NEM a relatively new framework as of March, which allows for us to declare what we call an indistinct event. So that's where there are conditions that could impact the power system where we can't identify the specific asset that would be impacted. So we can't say it's line 1 or line 2. It might be any one of 10 lines that could be impacted by a particular event, whether it's a geomagnetic storm, a lightning storm, or other event. And we can take measures to operate the power system to bolster its resilience in real time. And then the final one there in the operational time frame, which sort of links to the risk review, is protected events. If we've, prior to the operational time frame, declared a protected event, then in the operational time frame we can take measures to operate the power system to improve its resilience. Similar measures to the other 2 in the operational time frame. It generally means we would be constraining flows on corridors or cut sets in the power system. And then the third element I wanted to touch on in terms of how we go about managing these major events is that we have quite detailed processes and actually quite clear obligations to investigate and report on major events that occur. and so we will undertake a detailed review of events which are considered to be of significance to the operation of the NEM. Now, before we sort of dive into the risk review body of work itself, I would like to just spend a minute or two on the risk assessment approach, and hopefully for the attendees there'll be some things which resonate and which might even be useful to consider in your own approach if you're a system operator or an operator of any kind, really. So what we're showing here is the bow tie risk assessment approach, and in the center of the bow tie is the hazard. A hazard could be operations, activities, or situations, and a hazard has the potential to cause harm, but cannot do so if adequate controls are in place. When control of a hazard is lost, a normal situation changes to an abnormal situation, and in the bow tie, this event or change is called a top event, so it's the center of the bow tie. For example, a top event could be a frequency excursion on the power system. To the far left of the top event are the threats, the things that could stop that event occurring. For example, a double circuit fault or a multiple generator trip could be one of those threats, and there could be various things that would prevent that, resulting in a frequency impact. On the right side, you then have the reactive controls, and they help minimize the consequence of the event. So what this is really useful at illustrating is whether the controls that are in place to avoid that event are effective, and indeed, if that event still occurs, are the reactive barriers adequate to minimize the consequence of the event. And we use this framework to evaluate our operational risks. It's important in the context of understanding how those risks are evolving with the transitioning power system and whether the controls in place remain effective. Another example would be how we manage system strength. So another example would be a protective barrier would be AEMO directing units to prevent us landing in a condition where we have too few synchronous generators online. If we still found ourselves in that situation, then some of the reactive barriers we would want in place are ability to adequately monitor power system's performance, have appropriate contingency analysis available, and so forth. And so the effectiveness of controls can change depending on the phenomenon that are relevant to the operation of the power system. So I'll move us on to the evolution of the risk review and basically just cover how that's evolved over time, what triggered the need for it, and the purpose. So the first power system frequency risk review was undertaken in 2017 and 2018 for the NEM in response to a rule change following the 2016 South Australian Black System event. Over time, the review has expanded to include events and conditions that could lead to cascading failures or supply disruptions, with the first annual General Power System Risk Review published in 2023. And we do so in accordance with excuse me, clause 5.20A of the National Electricity Rules. Next slide, thanks, Dan. The purpose of the risk review is to evaluate a prioritised set of risks, which comprise contingency events and other events and conditions that could lead to cascading outages or major disruptions to the power system, to evaluate current arrangements for managing the identified priority risks and the options for future management of those events, the arrangements for management of existing protected events and consideration of changes or revocation of those events, and the performance of existing emergency frequency control schemes and need for modifications. The way that we achieve that is by exploring the risks and consequence of non-credible contingency events, again, those high impact events, and other events and conditions that could lead to cascading outages or supply disruptions. We consider how those risks evolve over the 5-year planning horizon, taking into account changes in the power system, which we touched on in an earlier slide, and building on that and complementing other work undertaken by AEMO, such as Integrated System Plan, Engineering Roadmap to 100% Renewables, and in general AEMO risk management initiatives as well. I'll just touch on how we go about identifying those priority risks before I move to Dan to go into a bit more detail. Really, the starting point in our development of each risk review is to look at what's happened on the power system. What have we actually seen? Where have we seen operational challenges in how we manage the system? And where have we seen major events where there have been learnings from those events? A couple of recent examples just to highlight would be in November of last year, we saw challenges in managing the minimum synchronous generator operation in New South Wales. And that demonstrated the potential for those challenges to evolve over time as we move to fewer synchronous generators online in New South Wales, and flagged to us some of the challenges we'd need to manage. Similarly, just last month, on the 13th of February, there was a major storm event in Victoria, where I'm based, where 6 500 kV towers collapsed associated with that storm, and that led to a series of events in Victoria, which again highlighted some of the risks that we need to consider in evaluating the potential for cascading faults. The second element is to really engage with our internal teams across the whole business, as well as the network service providers who own the physical assets in each jurisdiction of the NEM and plan the development of those assets, to consider known risks and controls through extensive engagement with network businesses. We undertake cross-departmental brainstorming sessions to consider not just what do we know, what have we seen in the past, but what are the things that could arise in future. And then we evaluate the risks and calibrate those as well. The table here at the bottom of this slide, simplified for illustrative purposes, but the type of information that we're collating here, it relates to the events, the likelihood and consequence of those events, and the mitigations, both current and planned. And this helps provide a systematic way of identifying the priority risks that we then might evaluate in greater detail through the general power system risk review. Naturally, we can't look at every double circuit fault or every triple circuit fault for that matter, or station trip. So we focus our efforts on those events and conditions that have that potential to lead to cascading failures or cascading or supply disruptions in the NEM. Just building on that slightly, so in terms of the process that we follow, we develop a approach paper which describes the proposed risks, the risk assessment approach, modelling approach, and consultation approach. We consult widely with industry on the approach paper, and then ultimately undertake the general power system risk review, including all of the studies for those priority events, as well as any discussion around other events and conditions relevant to the general power system risk review. Okay, I think we're over to Dan now to go into a bit more detail around the simulation study methodology.
Hey, thanks, Luke. Yeah, so for this next section, we'll just discuss the methodology that was taken to conduct studies as part of the risk review, and we'll get into a few of the details of the modelling. So I guess to start with, we'll just talk about some of the factors that we consider when we're determining what modelling approach to take. And basically, depending on which risks we're going to be studying, that will determine which factors we take into account. So this slide contains a brief overview of some of these factors, such as the time frame of the study. So if we're looking at a current risk or a future risk. Sorry, I've just... Luke's just asked if I can have my camera on. I don't actually have that option because I'm sharing the screen, I think. We might have to leave the camera off, Luke, unless there's some other way that we can turn it on. Okay, so yeah, so depending on the time frame of the risks is going to determine which models we use. So if we're studying risks in the current system, then we can use historical dispatches from our OPDMS system. Or if we're looking at future risks, then we'll have to project out conditions and dispatches that we'll study. Similarly, depending on the phenomena that we're trying to study, that will determine if we'll use RMS or EMT tools to perform our studies. Say if we're looking at a small number of cases related to system strength and inverter-based resources, we're more likely to use EMT tools. But if we're required to run lots of different cases related to more classical power system issues, then it's probably more likely that we might be using RMS tools because it'll be more time efficient and it should be sufficient as well. Finally, in our study approach, we've also got a simplified model and a full NEM model that we can choose from. So because the GPSRR is a yearly process to identify risks, develop models, perform studies, and analyze report on the results, we need to have a focused effort on where we can get the best return of investment of our time for the year. So for studies that require high accuracy, we're likely to study a small number of cases in the full NEM model, but due to the added detail, it'll take longer to develop the cases, tune them, run them, analyze them, etc. But if we'd prefer to do a larger number of screening studies or things that are primarily frequency based, then the simplified model may be more appropriate. Okay, so this is discussing the full NEM model in a bit more detail. So if we're studying risks that are present in the current system, we can generally use the full AEMO NEM model fairly easily. So from the AEMO Operations and Planning Data Management System, or OPDMS, as we might refer to it, we can download PSSE cases that are aligned with historical dispatches from the system. So we have half-hourly intervals where cases can be downloaded, and these PSSE cases will align with the generation, load, interconnector flows, machines online, and many other factors for the time specified. In addition to this, for the risk review studies, we add in additional dynamic models to improve the accuracy of our simulations. So we'll add in composite load and distributed energy resource models so to more accurately represent load and DPV shakeoff and the response to faults. We'll also update governor settings or use generic governor models where accurate governor models aren't available in the OPDMS system. We can also add in under frequency load shedding and over frequency generator shedding schemes if they're expected to operate for the study, and also any other system protection schemes that might be relevant to study as well. So I'll just go into a little bit more detail about the composite load model. So this was used in our studies to model load response. And the importance of this is that it captures load shakeoff in response to large disturbances. The composite load model consists of 6 load components, and these include three-phase induction motors, A, B, and C, that have varying inertia, impedance, and torque properties. 1 single-phase motor D, which is a specially developed performance model based on lab tests representing refrigerator compressor motors, which are prone to stalling behavior, though this component's believed to be small in Australia. A static load, which is represented by a zip model. This doesn't have any tripping parameters, but will scale the active power with the bus voltage. And finally, a power electronics component, which includes undervoltage tripping behavior, but apart from that is relatively insensitive to voltage or frequency. So in addition to the composite load model, we've also added in the DER models. And so what we can do with these is we can add in distributed photovoltaics at each bus individually. The amount of DPV inserted can be varied to match the historical dispatch for a certain date, or we can specify a percentage of online DPV. So the DR-AEMO1 model is highly sensitive to voltage and also has some frequency dependency as well. And it's originally based on the DRA model developed by the Western Electricity Coordinating Council. However, it also has a few features additional to the DRA model, such as those listed on the slide. So partial power reduction following an over or under frequency event, representing DPV tripping due to frequency over 26 independent stages. Partial power reduction following a low or high rate of change of frequency event, representing fractional DPV tripping over 3 independent stages. Asymmetric reactive power voltage control, so separate proportional gains in response to under or over voltage conditions, and a flexible voltage reference, such that the under voltage and over voltage tripping behavior scales independently of the initial transmission bus voltage. And I've provided a link there with some more details if anyone's interested in that. As mentioned before, we've also updated the governor models in our studies. So when considering primary frequency response in the risk review studies, AEMO has proponent-provided governor models for a large number of the machines that include site-specific settings indicating the primary frequency response. However, in some instances, the site-specific information isn't available or it may not be up to date, meaning that the performance of that machine could be overestimated or underestimated. To manage this issue, AEMO has developed generic governor models as part of the 2022 PSFRR process to represent typical steam, gas, and hydro turbine frequency responses. These models were used in the PSFRR and GPSRR studies for units where the generator supplied governor models don't have the updated PFR settings in the OPDMS, or AEMO does not have a governor model in the OPDMS. So by developing these generic governor models, a more realistic and consistent approach can be used. And we can ensure that the correct PFR settings that meet the primary frequency response requirements could then be implemented. So this includes, for example, that the droop at the connection point must be set to less than or equal to 5%. When operating at maximum power, we don't expect any further frequency raise response from the generator, and the primary frequency response deadband should be no wider than plus or minus 0.015 Hertz. So the generic models were customized for each generator by adjusting the maximum and minimum power output limits, and the following PSSE library models were adopted, as you can see there on the screen. Okay, so in the risk review studies that we undertook, we also consider relevant remedial action schemes or special protection schemes involved in the risks that are being studied. So if there's a chance that the scheme may maloperate or lead to cascading failure, or even if it'll just operate as part of the risk that we're studying, then we'll implement that into our models as well and include it in the risk review studies. In addition to studying the impact of remedial action schemes in our risk review studies, AEMO has also developed the Remedial Action Scheme Guidelines. So the purpose of these guidelines is to provide a reference of good electricity industry practice associated with the terminology, design, modelling, testing, documentation, and review of remedial action schemes for the NEM. It's also to summarise relevant rules obligations for all the market participants in regards to the remedial action schemes. And because there's a wide range and increasing number of remedial action schemes across the NEM, as the power system transitions, there's increasing potential for failure to operate or unintended operation of the remedial action schemes that could lead to adverse system impacts such as cascading events and supply disruptions. In the context of the transforming power system and changing operational conditions, it's important that such schemes are reviewed to ensure they remain effective and continue to meet their design and performance requirements. So these guidelines have been designed to address these issues, and I've also provided a link to those on the slide there too. So we were talking briefly before about how we conduct studies in the full NEM model for current risks, but if we're looking at things in the future, it's a similar process, but there are a few key differences. Firstly, we can't rely on the historical half-hourly dispatches that we were talking about downloading before if we're studying future scenarios. We expect the loads going to grow in the future. We'll have new generation connecting, more customers will be installing solar, and that will also experience a retirement of existing generation. So all of these things contribute to different dispatches, and due to the many factors, we can't achieve this by just linearly scaling values upwards or downwards, because there's a lot of different factors to consider. So due to this, we use the latest integrated system plan Plexos forecasting data from the step change scenario to base our dispatches on. More details on this process can be found in the integrated system plan, but essentially this scenario is considered by energy industry stakeholders to be the most likely scenario to play out. Based on the risk that we're studying, we'll choose data that aligns with the risk conditions, such as if we want to look at high or low NEM demand. We might be looking at low synchronous generation dispatch if we're studying a minimum system strength risk. We might look at cases with high solar, high rooftop solar online, things like this. In addition to different dispatch data, we also have to integrate new augmentations to the network, including new generation interconnectors, transmission augmentations, new renewable energy zones, and many other things. So if we're performing future studies, these all have to be added into our models and considered when we're doing the dispatches as well. So the other option we have is we have a simplified model, and this is handy if we have large numbers of studies that we want to conduct, or it is more simple if we're looking at future risks. It's a lot more simple to redispatch a simplified model than it is to redispatch the full NEM model, as we were discussing before. So for the simplified NEM model, the following network configuration and modeling approaches were used. Each of the mainland regions are represented by a common high voltage bus, and all the regional generators were assumed to be connected to these regional common buses through appropriate generator transformers. Regional generators were lumped as steam, gas, hydro, wind, and solar with appropriate generic models, such as the alternator, voltage controller, governors, and IBR controllers. We also had the under frequency load shedding and underlying DPV were grouped according to their frequency trip bands and connected at the 33 kV distribution level buses, and then connected to common high voltage buses through appropriate transformers. And some areas of interest were still modeled in more detail if it was an area that we were particularly interested in. So as discussed previously, in certain circumstances, we can obtain more information to make recommendations from a wider range of studies in a simplified model than we would from a limited number of detailed full NEM model studies. So due to this, it's important for us to understand the benefits and the limitations that they provide so that we don't apply the simplified model if it's not appropriate. So this shows a few of the benefits and limitations here. On the benefit side, we've shown in benchmarking studies that it provides a reasonably accurate frequency response. So for studies where we're primarily interested just in the frequency, such as under frequency load shedding screening studies, then this is going to be a lot easier to set up and redispatch cases for. In addition to this, benchmarking cases can be run in the full NEM model just for a few cases if we want to compare and understand the error margin. But then we also have to be aware of any limitations. So because the network, the model excludes actual network impedances aside from interconnectors, it can't accurately predict power system voltages throughout the network. It also provides an approximation of fault ride-through characteristics of IVR plant, and it provides an approximation of the voltage-based tripping behavior of DPV. So, but we can get around some of these things. So for the future studies using the simplified model, the voltage response of DPV can be emulated by force tripping a fixed percentage of regional DPV based on findings from AEMO's previous studies. So as long as we're considering the risk in particular and how we're applying the model, then I think that applying this simplified model can provide some benefits. And so just showing here some of the benchmarking results. So these benchmarking results are contained in the 2023 General Power System Risk Review appendices. So you can look there if you want to find out more details of all the things considered in here. But you can see from a frequency perspective, the frequency response is quite close, both for export and import cases here. In addition to running RMS studies, we also undertake EMT studies using PSCAD, where it's deemed necessary to investigate the risks being studied. So to study these risks, we use the NEM mainland PSCAD model, which is a model that's comprised of the 4 NEM mainland regions of Australia, which is New South Wales, Queensland, South Australia, and Victoria. And this model contains all transmission network elements and key distribution network elements, and the majority of generator and network support devices are modeled using dynamic site-specific representations. It takes longer again than setting up the full NEM PSSE model. The PSCAD model takes longer again, so we have to determine whether we want to focus our efforts in the PSCAD studies just by verifying a few of the results of PSSE cases where we want to understand the behavior of IBR in more detail, or if we're looking at system strength, we could be studying a unique scenario for a few cases in PSCAD. And I'll just talk briefly about some of the success criteria. So for the risks that we're studying, we want to achieve the following success criteria. If we're looking at a credible contingency event, the voltage should not rise above the line shown in the figure here. So that sort of shows what the voltage response should be in the time after the fault. While for a non-credible contingency, it's more lenient in that time responding to the fault, but it has to return to plus or minus 10% of the normal voltage. In terms of frequency, we're looking to maintain the frequency within 49 Hertz to 51 Hertz for a credible contingency and 47 Hertz to 52 Hertz for a non-credible contingency for the mainland system. For oscillations in the system, we want adequate damping. So the halving time of any oscillation should be less than 10 seconds, but to account for planning and operating uncertainties, we aim to achieve a halving time of less than 5 seconds. And we're also looking at all the performance of the generators, including fault ride-through, capability of the IBR units, and distributed PV disconnections. So to be successful, we don't want the loss or instability of any interconnectors. We don't want to see any cascading failures, and we want all emergency frequency control schemes to operate as intended. And we're looking to ensure the PSSE or PSCAD simulation successfully completes as well. So that was a bit of a background to the methodology, but another part of the risk review process is that we do benchmarking of our modelling approach against real power system incidents. So one of these incidents was the Callide C4 turbine generator failure on the 25th of May 2021, as shown in the picture, where an initial issue at Callide resulted in cascading failure, the trip of multiple generators and lines in central Queensland, and the operation of more than 2 gigawatts of associated under frequency load shedding. So this was an interesting incident, but unfortunately, discussion of all the incidents that occurred is outside the scope of this presentation. So if you're interested in the specific details, you can have a look at the reviewable incident report in the link on the slide. But as we can see here, we did some benchmarking of our models against the actual event, and you can see the frequency response there. So we can see that the simulated and measured frequency are quite closely matched, with a difference in the frequency nadir of approximately 0.15 Hertz. So I think that gives us more confidence in our models. And if we do ever find anything that doesn't align, then we have a continual improvement process for our modeling approach. Okay, so I'll just briefly talk about a study example, just to give you a bit of an understanding of the things that we do look at. But more details on this can be found in the relevant GPSRRs and PSFRRs. So as Luke briefly mentioned, the NEM is a long and stringy interconnected network, and we have double circuit interconnectors that transfer power between the major load centers as shown on the slide here. The loss of one of these double circuit interconnectors can result in cascading failures across the NEM. And so this is what we were studying here. We were looking at Q&I instability, which is the Queensland to New South Wales double circuit interconnector, which is pointed out there at the top. This slide shows some of the results that we found just for one of the contingencies that we studied, and it found that if we were looking at non-credible loss of 2 lines between Victoria and Adelaide, so that's, as you can see, quite far away from Q&I, which is where the internet connector becomes unstable. This can lead to quite severe cascading failures around the NEM. So we see loss of 2 lines from the Moorabool terminal station in Victoria towards South Australia as the initial contingency. And then we see operation of a protection scheme in South Australia. We also see the Haywood interconnector to South Australia opening. We see instability on Q&I, which trips. And then, as you can see in the picture here, the NEM separates into 4 frequency islands, and it's quite a large cascading failure. So the thing is that this was only one example, but we saw this or similar responses for lots of different contingencies, such as the loss of a large amount of load or generation in Queensland, the loss of large generation in Victoria, and a variety of other transmission line contingencies across the NEM that are non-credible. So the wider ranging impact of contingencies in the NEM make these studies important to undertake. And this is why it's important for us to have this overarching risk review that are looking at the impacts across different regions where maybe the grid operators of the specific, like the transmission network service providers, might not be looking at what a risk in their region might have on one on the other side of the country. Finally, completing studies is not the only part of the general power system risk review. In addition, we need to make recommendations based on the outcomes of the studies and implement solutions to reduce the likelihood or severity of potential risks. So for this risk that we talked about here, we recommended that the Queensland and New South Wales transmission network service providers design and implement an appropriate special protection scheme. And preliminary studies that were undertaken showed that this would be effective at preventing Q&I from losing stability. Okay, now we'll pass back to Luke.
Thanks, Dan. I'll just briefly cover some of the other risks. So Dan's talked about some of the priority specific contingency events considered through detailed analysis. There are a range of other risks and conditions that we consider through the body of work of the risk review. You all have the slide pack and will receive the recording after as well, so feel free to go through. But I might just call out a couple that we're presently focusing on in the NEM. They're actually both at the bottom of the page. One is SCADA failures, and we're doing a detailed review of recent SCADA outages, given the criticality of SCADA to the operation of power systems, and we've been engaging with the other GPST system operators around their experience as well. We're planning to publish a report on that in March, actually. And then managing system strength. I've touched on that a couple of times throughout as well, but thinking about going forward, how do we manage the security of the power system in the context of low system strength operation. On the next slide, just drilling into an example that we covered in the 23 risk review as well, relates to potential periods of high demand and the increasing outages that we do see as coal-fired power stations in particular approach end of life, and how we might look to effectively or efficiently mitigate those risks. So that recommendation sort of drew on previous experience around some periods of high demand we'd seen in the NEM where emergency generation needed to be deployed, and we could anticipate in future we might need emergency generation for both high demand, but also to provide other services such as system strength if we have forced outages on the remaining in-service synchronous generators in the system. Just on the next slide, Dan. So those recent examples are shared there. So back to 2016 instances where we've needed to deploy at short notice emergency generation. And on the next slide, it just describes some of the things that we think would be sensible to include in those contingency plans. I won't talk through all the points. I might hand back to Dan to wrap up, and then we'll move to QA.
Okay, thanks, Luke. Yeah, so just a quick wrap up, I guess, is to discuss the 2024 GPSRR, which is upcoming. So this is just a brief overview of the risks that we'll be studying in the 2024 GPSRR here. Essentially, we're looking at a double circuit outage of HumeLink, which is a new proposed 500 kV transmission line in New South Wales. So as we discussed with some of the previous ones, this could have the potential for cascading failure because it's planned to increase transfer capacity by up to 2.2 gigawatts. So loss of that will have a large impact. We'll also be studying in PSCAD a circuit breaker fail event, looking at system strength issues in Victoria. We'll be conducting a under frequency load shedding settings screening study in the simplified model to sort of feed information into a more detailed UFLS review that another AEMO team will be reviewing regional band settings and include recommendations about consolidation or updates to band settings for regions. And we're also going to be determining power transfer limits for the South Australia interconnectors under destructive wind conditions. Finally, we talk about other risks and conditions, a bit like how Luke was referring to. One of these that we'll be looking at, which will be of interest in this year's GPSRR, is the operation of New South Wales below the minimum unit requirements. So as we've sort of touched on, in Australia, we've seen a trend of existing coal units retiring. And with the upcoming expected retirement of Eraring in 2025, this will introduce problems operating while still maintaining the existing minimum unit requirements. So we'll try and discuss a few of the considerations that are required for this. Finally, we'll just finish up with a brief overview of the 2024 GPSRR timeline. So we're currently finalising studies from now until the end of March. And in parallel, we're analysing our results, writing the report and developing recommendations. Once we have a draft version, we plan to share this with the industry and do a formal consultation period. And we'll be aiming to publish the final report by the end of July 2024. So if you'd like to keep up to date with our progress, I've provided the link here on the slides, which details the GPSRR page. And if you have any questions or have any emerging risks that you've identified in your networks that you think we should be aware of, feel free to contact us via email at gpsrr@aemo.com.au. So thank you very much. And yeah, we might pass over to some Q&A.
Okay, thank you, Dan. Thank you, Luke. Nice overview of your approach to risk assessment in Australia. We've got a lot of questions, and I think I'll just jump right into them. The first one, I think Luke and I spoke about a little bit beforehand. The language non-credible contingencies has been misleading for some stakeholders on other latitudes. Have you considered aligning it with NERC's planning events?
Thanks for the question. Look, I suppose it's fairly embedded in how we operate the NEM to refer to credible and non-credible, but having a little bit of familiarity with the NERC definition, I think a lot of the things we're talking about, can be mapped. So circuit breaker fail events, from my understanding, would probably be a P4 type event, a double circuit fault be a P7 event, and so forth. So we could certainly, map the types of events we're considering to the NERC definitions, but I don't believe there's any plans to align or harmonise the specific definition Again, credible and non-credible fairly ingrained in how we do things in the NEM.
Yeah, do different things in
Mm.
different ways in different places.
Yeah.
Can you say a bit more about why you anticipate increasing remedial action schemes and how AEMO's thinking about remedial action schemes has evolved in the last decade or so?
Mm. I mean, remedial action schemes have the potential to improve asset utilization. So particularly where they're in place for credible events, it enables you often to more fully utilize the transmission infrastructure that you have, and particularly in weak or weakly meshed parts of the system, that can be a useful and cost-effective way of enabling energy from renewable connections to load centers. So I think for credible events, we're seeing some drivers. For non-credible events, or those, let's say, the P7 type events, if I use the NERC terminology, can be used to improve the resilience of the system. And again, something we touched on earlier is that we're seeing increased power transfer through these major corridors. And so you could anticipate that to improve the resilience of the system, you can leverage the technology and capability of these schemes, and particularly with things like WAMs, which are more sophisticated, and the technology that is behind some of the advances in remedial action schemes. There's the potential to actually improve the resilience of the system by leveraging that capability. I note there was another question in the chat about an upper limit on schemes. I think probably need to reflect on that a little bit, whether there's technical limits versus practical limits. Naturally, understanding the operation of the system, practically reviewing these schemes, ensuring that they're up to date, the settings are appropriate and fit for purpose, creates a range of challenges as well. To try and address that, what we've done is we've developed the remedial action scheme guidelines, which Dan touched on, to help define good practices for the design, and we've also defined some of the modelling requirements and actually starting to include those in our GPSRR studies, so that we're taking into account some of the key schemes that we do have in place in the NEM.
Yeah, often a bit of a challenge.
Mm.
So what applications are used to evaluate non-credible contingencies in real time and for immediate future time points? I presume that's software application.
I might start with an answer to that and see if Dan would like to add. In the planning time frame, we're using PSSE for our RMS studies and PSCAD for our EMT studies. In the real-time environment, we use PSSE, and we've got some in-house developed dynamic security assessment tools which are running PSSE as the analytical engine in the background. At the moment, for real-time application, that's for credible events only. We are considering expanding that to enable frequency modeling and also look at non-credible events as part of that screening assessment, but don't have that in place at the moment. And the other thing we're looking at the moment is developing some EMT contingency analysis using PSCAD. Again, that would be focused on credible events, not the non-credible type events.
Okay.
Dan, did you want to add anything to that?
No, I think you covered that excellently. Thanks, Lee.
Okay. The next question is, what role do the grid forming battery energy storage systems due to connect over the next few years play in managing the non-credible events?
Dan, would you like to take that one?
Yeah, sure. So, yeah, that'll be quite an interesting thing for us to consider over the next few years, and we have to make sure that we don't think that the grid forming BESS systems are going to be the solution for all problems. We have to make sure that it's considered, and we have to study these, and I'm sure we will as part of the future general power system risk reviews. We do see a lot of new BESS wanting to connect to the Australian system, and if it can, if our studies show that it can support it well, then that's going to be a good part of the solution. But we're also looking at having synchronous condensers, potentially converting existing generation to synchronous condensers, and other sort of measures to ensure that we have the system strength and inertia in the system that we can still operate it to handle non-credible contingencies. But I think definitely the fast response that that BESS can provide is going to be quite useful in the system. And so as long as it's considered properly, then this can be very helpful for, you know, special protection schemes and sort of these sort of considerations.
Okay, I think we'll try to squeeze in one more question here. In areas of high penetration of IBRs, what steps is AEMO taking to ensure the IBR control systems interact correctly?
I think, yeah, so this is going to be something that we're going to have to keep considering and keep studying, but it's essentially making sure that we've got an sufficient system strength in these regions. So a bit like what we were discussing with operating New South Wales below the minimum unit requirements, this is definitely something that will be considered in the GPSRR. How do we make sure that we have enough system strength so that all the new IBR that connects is going to operate as expected? So we do have a connection process where individual plants as they connect are tested and ensure that they don't cause additional harm, and they have the requirement to self-remediate, so provide their own system strength at an area. But if we have existing coal-fired or like synchronous generation that retires, then we might see a reduction in system strength across the grid. So it's definitely an issue that we're looking at, and one that we may have to make recommendations, sort of whole of system recommendations as part of this general power system risk review, where we might need to fast track installation of synchronous condensers to assist and make sure that we've got the required system strength so that the IBR will operate as expected.
A lot to think about.
Yeah.
Okay, we're just past the top of the hour, so we're going to need to wrap it up. And I want to thank Luke and Dan for this really informative webinar on the contingency analysis activities at AEMO. I think we all have a lot we can learn from them. As I mentioned earlier, an email will go out once the video file has been posted, and we'll answer the questions we didn't get to and get them posted as quickly as possible. We appreciate your participation, and if you would like to stay engaged, I'd like to invite you to participate in the next ESIG webinar on March 19 with Hannes Pfeifenberger of Brattle on transmission planning with HVDC. I'd also like to invite you to attend the ESIG Spring Technical Workshop in Tucson the last week of the month, featuring a great lineup of topics and speakers. Further information on all of our webinars and events can be found on our website at esig.energy under events, and you're all invited to attend. Information on all the GPST webinars can also be found at globalpst.org. Luke and Dan, I want to thank you again for this very timely webinar, and thank all of you for your interest. We look forward to seeing you again in the near future. In the meantime, everyone, take care, stay safe, and thanks again for your participation. Thanks, guys.